Thank you for the reminder. I often forget and then regret it when I'm halfway through. So this section is all about really roots and radicals. So square roots and radicals, and we'll learn those are really a type of exponent. And we're going to learn how to add them and subtract them and simplify them, just like we do with our other kinds of expressions. And then we'll learn to solve some equations with them. And then right at the end, we'll deal with these complex numbers. So in the beginning, just remember this: the square root of 9 is 3, and many of us just know that, right? The square root of 9 is 3, but there's a reason there. It's because 3 squared is equal to 9, right? So when we think about square roots, we're really thinking them as sort of the opposite or the inverse of squaring, right? So if some number squared is 9, then the square root of 9 is that number. So we go back and forth. And so that works fine for lots of numbers, right? Like the square root of 100 is 10, and the square root of 64 is 8, etc., right? And we just know those, hopefully, because of just our multiplication facts. But then we start thinking about some other numbers. And what about the square root of -9? Well, I don't know in the beginning really what that would be, because any number that we're used to when we square it isn't going to give us a -9, right? Real numbers, when we square them, give us positive values. Whether this is -3 or +3, when I square it, I get +9. So I don't know what this is, but it's definitely not a real number. And that's how we're going to start when you begin these problems. Your answer there will be not a real number when you have the square root of a negative. But near the end, we say, well, okay, if it's not a real number, is it maybe some other kind of number? Is there some other number that when I square it gives a negative? And once we have that idea, we can make that happen. And that's really one of the kind of powers of math, is that we can take ideas and turn them into reality. We're not constrained by anything but our kind of imagination. Imagination sounds fake, but these are not. They're called imaginary values, but the name is misleading. The name makes them sound like they're not something actual, but they are numbers just like other numbers. Sorry, not the square root of I. Square root of -1, we're going to call this value I. Sorry, I don't love the way the pencil is showing up. Pen will be better. So this is our definition of what an imaginary unit is. The square root of -1 is I, and that means that if you square I, you should get -1. And I is called the imaginary unit. And again, that name imaginary comes because it's not a real number. It's kind of like a bad math joke, actually, but that's not my thing. It's kind of math puns and stuff, but it is what we call it. So imaginary unit, but don't think of it really as anything different. It's just a value. It has some special properties, right? And these are its special properties. So once you understand and introduce this imaginary unit, well, then I do know a number that when I square it gives me -9. The 3 squared would give me 9, and the I squared is going to give me the -1. So 3i squared is 3 squared times I squared, which is minus 1, this part, and 9. So that gives me minus 9. So since I have a number squared that gives me minus 9, the square root of minus 9 is this value 3i. Okay. So there's some substantial conceptual ideas here with imaginary numbers, but the good thing is in the beginning, they don't have to be very hard for us to work with. The rule is whenever we take a square root of a negative, that negative becomes the I. And then the square root of the number becomes the numerical part, right, that's left over. Does that help with that original question? I think it was the square root of minus 100. Since it has a square root of a negative, that's going to be an I, and then the square root of 100 is 10. So that would give us 10i.
What if it's square root of negative 80?
Okay, so again, we need a little bit of background to get here. These this involves a little bit from some of the previous sections. The square root, what you can do with the square root is I can take the square root. So here's a rule for square roots. The square root of a times b is the square root of a times the square root of b. So what that says is I can take the square root of kind of each part separately. So when I look at negative 80, I could start by seeing it as minus 1 times 80. And I know the square root of minus 1, that's going to be I. So I'll write it out here because this is kind of our first time. That's the rule. The square root of a product, I get to take the square root of each piece. The square root of the minus 1 is I. Now, the other part is the 80. So unfortunately, unlike our previous examples, the square root of 80 is not a perfect square, like 9, right? Square root of 9 is 3, because 3 squared is 9. But we don't know a number, not a regular integer, whose square is 80. And I know some numbers that are sort of close, right? 9 squared is 81. So this is going to be pretty close to 9, but not quite. What I can do is I can kind of use the same trick, right? I broke negative 80 into 2 factors, and I knew the square root of one of those factors. 80, it turns out, is 16 times 5. Now, it's also 20 times 4 and 2 times 40, and there's lots of other ways of factoring 80. But 16 is a really good number for us because we should know the square root of 16, right? The square root of 16 is 4. So when I rewrite 80 as 16 times 5, that's going to allow me to take the square root of 16 when I break this apart, and then the square root of 5. The square root of 16 is 4. I like to write the 4 in front of the I, just like an X, right? We prefer 4X over X4, but they do mean the same things. And then the square root of 5 is a little bit of a question. Like, I don't know a number that's exactly the square root of 5. You can estimate it on your calculator, but if you estimate it, you're not getting an exact answer. You're going to get a decimal that it turns out you have to cut off somewhere. So what we want to do in this case is just leave it as an exact answer. So I'm going to leave this square root of 5 part inside the radical still. So when you think about a radical, the inside part is the operation is being applied to that inside part, the square root operation. I'd like to pull things out, which means doing the square root. So I did the square root of -1, and so I get I, right? I don't need the square root anymore because I did it. Same idea here with 6 square root of 16, right? I can do the square root of 16, so I get 4. No more square root needed because I did the operation. Right? I mean, you do that all the time, right? If you do 3 squared, you get 9, and you don't leave the squared there, right? Because you already did the squaring, right? That's what got you the number. Same thing here, right? When I take the square root, I don't need that symbol anymore because I've already done it. But the 5 part, I wasn't able to take the square root of, so I have to kind of leave it inside or leave it as the square root of 5. Are there questions from anybody else about this kind of problem? If you're feeling a little shaky on it, that's okay. It is this one's actually like at the very end of our section. But it is using this idea of simplifying a radical. So the I part, it's there, and you'll see some problems with it, but it's really the simplifying the square root of 80 that turns out to be the kind of the most important type of problem throughout this whole chapter. Let's see another example that's kind of similar to that. The square root of 75. Well, again, there's nothing that is exactly the square root of 75 that we know, a nice integer number, that's the square root of 75. So I want to see if I can simplify it, kind of get it as close as I can. And to do that, I want to factor 75. It does turn out that it's 15 times 5, but that's not very useful because neither 15 or 5 are perfect squares. A much better way to factor it is 25 times 3. And you're just looking, there's no magic here. It's just you're looking for these perfect squares. So I'm thinking, are there factors of 4 or 9 or 16, 25, 36, right? Those are our most common squared values. I'm looking for those factors within each problem. And now, just like before, I can take the square root of 25, which is 5, and I can take the square root of 3, which is the square root of 3. It's a number, the square root of 3. It's like 1.4, 1, 2, 3, 17. It's just a decimal that goes on and on forever, but it's somewhere around 1.4. 1.6, maybe, I can't remember exactly, but it's a number. So this is 5 times that number. This is just a simpler way of writing the square root of 75. Any questions on these? Let me do one more, or 1 or 2 more.
I
Yeah.
have a question. So if So if the number in the square root is let's say like how this one is 75, do you use like the largest perfect square root square factor?
Yes, that's a good question. So in this case, there's only one, which is 25. But actually in the last problem, 4 is a perfect square factor of 80. So you could have thought of this as 4 times 20. That's also 80. And the square root of 4 is 2. The problem here is that there's still another perfect square factor inside 20. So you would have to continue and write that as 4 times 5. Take the square root of 4 and you get 2 times 2 times the square root of 5. And then you do get the same thing, 4 square roots of 5 in the end. That's for the 80 part, right? Ignoring the I part of this one. So it's much nicer to pull the biggest perfect square first. So instead of 4, 16 is a better option here because then I get my answer kind of all in one step. It's not wrong if I do it the other way at all. I just sort of have to keep doing it till I get all the perfect squares out. So that doesn't come up that often with numbers just because the numbers get really big. This is really like 2 to the 4th, 2 times 2 times 2 times 2. If you do 3 to the 4th, you get 81, but anything bigger than that starts to get really big. So you don't see this too often with the numbers, but yes, your goal is to pull out as much as possible from the radical. Does that answer that question?
Yeah, thank you.
Okay, yeah, that's a great question. Certainly that will help. If you're getting one wrong and you pulled something out, you might want to look back at what's left over and make sure you pulled everything out. That is more common actually with these kind of next problems I wanted to show you. I'm kind of working, let's say, like a little bit backwards through our section. So we kind of started with a little bit at the end, these complex numbers, and then we're moved into simplifying these radicals, which is, I think, homework 3 or 4. But it all works still. Let's look at the square root of x to the 6th. So here, it's a little different than before because x to the 6th is an exponent. So it is not that I'm taking the square root of 6. I'm taking the square root of this x to the 6th. And remember, x to the 6th is x times x times x times x times x times x, right? X to the 6th. And so I think when you look at it that way, you can kind of see what the square root must be, right? This is x cubed times x cubed, right? So what squared gives me x to the 6th? Well, it's x cubed squared, right? X cubed times x cubed. So this is really x cubed. Since if I square this, remember your rules of exponents here, 2 times 3 gives me x to the 6th. That's what it means to be the square root, right? If I square it, I should get back what I started with. So the exponents here are working a little differently than the numbers were, right? We don't have a square root of 6. That's not a number we can simplify at all. But we do have a square root of x to the 6th. Okay, so exponents are very different things than just the values. What about the square root of x to the 10th? I don't really want to write this out like I did the last one. I could, I suppose, but we can use our mind's eye to figure out what this must be, right? The square root is sort of breaking it into two equal pieces. Each of those equal pieces is x to the fifth. And the hope is that you might have even noticed like a little shortcut here, right? Like what if I had square root of x to the 20th? I actually don't even really need to think about writing that out and splitting it into pieces, because I think you can see that the square root is really dividing the exponent by 2. It's cutting it in half, right? Which is really just what we did up here. So what about the square root of x to the 7th? And this always how it goes in math, right? Figure something out, it seems reasonable, and then right away we move into something where it doesn't work anymore, right? It's because we make assumptions when things work one way, and then when we start to see other ways that it doesn't work, we start to view the problem from different angles and different perspectives, and then we start to fully understand a little bit more of what the problem is. So here it doesn't work because x to the 7th, you can't split exactly into two pieces. You can't take its square root as it is directly. So just like the previous problems with numbers that we were doing, I want to split x to the 7th up into a perfect square part and a kind of leftover part. And this is where we want to make sure to kind of pull out as much as possible. So the right way to factor or break apart x to the 7th is x to the 6th times x. And I do that because I know the square root of x to the 6th, right? We already did that one up here. Taking the square root is like dividing it by 2, dividing it in half. I get this answer, this simplified answer. Notice I say, it's like dividing it by half. That works when we have a multiplication like this, right? Like 3 things multiplied by 3 things. It is not like dividing the number 10 in half, right? That's not the square root of 10. That doesn't work that way with the numbers. But with products like this, which are exponents, that idea of sort of having works, because then that's what kind of squaring is, right? It's multiplying one thing times itself. So if you can break it apart like that, you are taking its square root. And please hop in, jump right in if you have any questions about any steps here. So here I'm kind of jumping a little bit. We haven't formally defined the cube root, but it's same idea as a square root, except instead of squaring, you have to cube the number to get it back. So maybe before we jump into x to the 7th, like the cube root of 8 is 2. Since 2 cubed, 2 times 2 times 2 gives us 8. So this is the definition of a cube root. Can we take that idea and apply it to this problem? A square root cut the exponent in half because I needed 2 equal pieces. A cube root is going to cut it into 3 equal pieces, so it needs to divide it by 3. Again, x to the 7th is not divisible by 3, but x to the 6th times x certainly is. Don't forget the cube root there. It is important. If I don't write that there, then it's a very different problem. So the cube root of x to the 6th, the cube root here is going to divide that by 3. And I'll get x squared. And then I get the cube root of x. Separate thing. And remember your rules of exponents. If I cube x squared, I multiply those exponents back together, and that gives me x to the 6th. So x squared is definitely the square root of, or the cube root of x to the 6th. What we're actually doing is kind of developing a definition of a, well, it's called a rational exponent, kind of in reverse here. What do you think? Let's use 25 to the 1/2 power is. And we haven't seen these fractions or rational exponents. But it turns out they follow the same exponent rules as before. So we would multiply this exponent times any exponents here. And you may notice that that's really kind of what's happening in these problems up here. Instead of the square root, what if I wrote that as the 1/2 power? Well, then you'd multiply 1/2 times 20 and you would get x to the 10th. And notice here, x to the 10th to the 1/2. If I use my rules of exponents, that would take me back and divide that x to the 10 by 2, which would give me 5. So what we can do is make a definition of what a rational exponent means, and it really means a root. So 25 to the 1/2 is the same as the square root of 25, which of course is 5. 8 to the 1/3, you may guess, and you would guess correctly, that is the cube root of 8, just 2. And in general, anything to the 1/n is equal to the nth root of a. This side here is called a rational exponent. And this side over here is called an nth root, like a cube root or a square root or fifth root or whatever root you end up with. So I think homework 2 involves working with these rational exponents, taking a rational exponent and changing it to a root, taking a root and changing it to a rational exponent. And we can be a little bit more versatile with our definition.
Sorry, I
Yes.
have a question.
Great.
This is off topic of what you're teaching, but about the final, is it gonna be from the start of the semester to the end, or just where we kind of left off?
Yeah, that's a good question. And maybe you're thinking that as we accumulate more and more ideas and information, right? It starts to feel like a lot. It will include some information from the first part of the semester, but I restrict that to a pretty small set of things. And about 75–80% of the final is on the new material. So the material since the midterm. And I'll lay out, in some detail what the the sort of ideas I want you to know from the first part of the semester. And some of those are things that we've been using throughout the whole semester. And so they're, like solving linear equations. That's sort of something that we keep running into in all of our sections. So you may have, worked hard to learn it in the beginning, but since we've continued to use it, hopefully that's something you're better at. And the same thing with factoring, right? Like we learned some factoring, but we've continued to use it throughout these sections. And so you end up that you've improved quite a bit with those factoring skills. So that's kind of how that's structured. So I do understand it is a lot of information to do all at once. We're focusing on the new material. And yes, I do allow another note sheet again for the final exam. You are welcome to bring that in. I guess I have your, good question. I have your note sheets from the midterm. If you want those back, I can get those to you. I can scan them and email them to you. So just if you do want those back, just send me an email and I can scan it and send that back to you. And on the final, I'll allow 2 sides, so you can, print off that one from the midterm if you want, and then just add new stuff to the back side for the final. Okay.
Oh, so we can use front and back for the finals?
I allow for the final, I allow front and back, sort of thinking like, well, you already made a note sheet for the midterm. I don't need you to recreate that for the final. You could use that and then, put something on the back or 2 front sides if you want. It's okay. But so like 2 total sides of a piece of paper.
Okay.
Okay. So this definition here, and this is probably something you'll want to write on your note sheet, allows us to deal with kind of other types of rational exponents. There's not an arrow here, but these are related formulas. This is saying what happens if we have a numerator. The numerator just ends up being like a regular power. The denominator is the root, the sort of part that reduces the number. The numerator is a normal power. So, for example, 8 to the 2/3. So the denominator is 3. The numerator is 2. So I take the cube root of 8, which is 2, and then I square it. So that 8 to the 2/3 is equal to 4. You will also see some questions in that rational exponents that look kind of like this. X to the 4th times y squared to the 1/2 over x to the 2/3. So these are just like our exponent problems that we saw back, I think that was section 4, where we reduced the exponent problems. The only difference is that these involve some fractions. So they're a little harder because working with fractions is a little harder, but the process is exactly the same, which is good because we've already worked on that process, right? We start by applying that exponent to both of these and we multiply those. So 4 to the 1/2 is 2. 2 to the 1/2 is 1. We don't normally write the 1 there, but and then I have x to the 2/3. So that gets rid of the parentheses. And then I want to combine the x's together. And I do that by subtracting the bottom exponent from the top. And so this is where we just have to do a little extra work because it's a fraction, right? So in order to do that, I want to remember that I can rewrite 2 as 6/3, and 6/3 minus 2/3 is 4/3. So that gives me x to the 4/3 times y. And when your problem starts with rational exponents like this one does, definitely leave your answer in rational exponents unless it asks you to write it as a radical. Right? So if I had to, I could write this as a radical. This is the cube root of x to the 4th times y. It's not really better than the rational exponent part. But so this is rational exponents, and this is a radical. So there's a little bit of converting back and forth. Those are a couple of the problems. Most of the problems are using these sort of exponent rules again, just now with fractional exponents. So again, it is similar to what we've done before, but you do have to do a little bit of operations with the fractions there. Questions on that? I want to just go back again to the radicals and simplifying the radicals. In many ways, that's the most important operation from this section. A lot of the later work that you do in this section requires you to simplify the radicals. So if you can't simplify them properly, then you don't end up being able to do all the later sections too. So I think this is the 3rd section, and then like the 4th and the 5th section, you need to be able to simplify those radicals. So I just want to kind of take another look at a couple of these. The square root of 8x to the 11th, example. And I'll do one more example. Let's try the cube root of 24x to the 14th. Our goal in both of these cases is to pull out as much as we can, which means taking the square root or taking the cube root of the largest possible perfect squares or perfect cubes. So when I look at the top one, the nice thing is you can just look at the numbers and then look at the variable parts separately. They don't really interact with each other. So when I look at 8, I know that one is 4 times 2, right? And the 4 is the perfect square part. The 2 is like the leftover part. I like to write them like this, and you'll see that if you look at my videos on D12. You don't have to do that this way. It's just a way of kind of organizing. X to the 11th, we remember that the square root divides exponents by 2. So the biggest way I can break that up is to put x to the 10th in the perfect square part and the other x in the end, right? So if I multiply this together, I get back what I started. but I've divided it in a way that I can take the square root. Square root of 4 is 2. The square root of x to the 10th is x to the 5th. And then this square root, I'm not able to take it, so I have to leave it on the 2 and the x. And this is the reduced or simplified expression that we're looking for. All right, here's another one. This is now a cube root. So the difference here, 24 is definitely 4 times 6, but that's not helpful with the cube root. With the square root, 4 times 6 is a nice way to factor it. But with a cube root, 4s are of no help, right? With a cube root, I'm looking for an 8. So I want to factor this one as 8 times 3. And of course, it also changes how I break up the power of x. So x to the 14th, I'm going to divide this exponent by 3. And 14 doesn't divide evenly by 3. So I need to split it up. The best way to split it up is to put 12 of the x's there and 2 x's left over there. Cube root of 8 is 2. The cube root of x to the 12th, I divide that by 3 because it's an exponent. I get x to the 4th. Then I have a 3x squared, still under the radical.
I have a question.
Yes, great.
You said 4 to the 6, right? So this one is saying 3 cubed, 24 times 14, right? So what's the 4?
So I'm rewriting 24 as 8 times
Yes.
3.
Okay.
And I'm doing that because I'm looking for the perfect cube, which is 8. So
where does the 6 come from?
so the 6 would be like from a bad way of factoring 24. So, 24, you can factor it in lots of ways. One way is 4 times 6. But that's not helpful when I'm taking a cube root.
Okay.
Instead, I wanted to factor that as 8 times 3 for the cube root.
So if we say we remove the 6 right there, so we use the 8. We say 4
Instead
times
of
8.
Yeah, instead of 4 times 6, I'm choosing 8 times 3 because I'm looking for perfect cubes.
Okay.
If my problem was this instead, the square root of 24, here I had the cube root of 24, but this one is the square root of 24. That one I would want to factor as 4 times 6.
So since that one is not the perfect way, then we're using 8 times 3.
So we're using the 8 because 8 is a perfect cube.
Oh, okay.
But here we're using 4 because I'm looking for square roots.
Okay, I understand.
So it's like some numbers you can split up in different ways, and you're going to do it differently depending on what that's called the index, what the index is. So cube roots are similar, but they definitely work differently than square roots. The perfect cubes you're looking for are almost all of them are 8 and 27. So 8 is 2 cubed, 27 is 3 cubed. They start to get very big afterwards, so we don't see them very often, but 64 is 4 cubed. I guess you could see some 125s, sorry, not 4 to the 4th, 4 cubed, which is 5 cubed. That's probably as big of a factor as you will see in the problems, and certainly as big as I would ever have in a problem. So these are the factors you're looking for when you have a cube root.
Okay.
So if I give you like the cube root of 81, so you're just looking for these factors. If you don't have one of these factors, then you're not going to be able to simplify 81. So 8 certainly doesn't go into 81 because it's not even. But 27, it turns out, does go into 81. It's 27 times 3. So that's where, like, when you're doing these with cube roots, I'm not just trying to break it down however I can. I'm only interested in breaking it down if I can have a perfect cube factor. If I don't have one of these perfect cube factors, then I'm done. I don't have to simplify it. But if I do have one of those factors, I can make this a better reduced kind of problem. So it's a good question. I'm glad you asked that. Other questions? This, like I said, the simplifying radicals is a very important skill to master. It makes the rest of the work with radicals go pretty smoothly if you're able to simplify these. So we do need to do the work with the rational exponents, these kinds of problems, but you don't really see those later on in the section. They're in this one chapter or one section, but that's kind of it. The simplifying radicals you see in a number of the remaining sections. So that's one to make sure you put some effort into and figure that one out and ask more questions. And it is very much a topic that for whatever reason, students that get it really get it, and they do well on all of the problems. Basically, occasionally we all make mistakes, right? But they do great. And then unfortunately, the students that don't get it really struggle. They don't get any of the radicals right, and then that really does hurt the results from this section. So it's a fairly unique topic in that way, that it really splits, and I want to make sure that all of us get on the right side of that split, right, where we feel good about simplifying those. And again, that's only going to come from some practice. If you haven't seen it or worked on it yet, some of this might feel a little shaky for you, but look at those videos on D2L. Get started on this homework early so you can ask questions and get help. And so that we can get you, be successful on this section. Like I said in the beginning of class, the schedule here is a little compacted because of both Thanksgiving and our kind of late work from the last section. So you've really kind of got a full week here for many of us to get most of the work done. I would much prefer that you can enjoy time with family on Thanksgiving if that's possible for you, rather than doing your math. So try and get it done before then, right? You don't want that hanging over your head. So that's what I was hoping to cover today, plus a little bit extra on complex numbers. There's a couple other little sections that we need to look at. We can talk about on Wednesday, but this should get you through the basics for a lot of what you need to do through this section. Okay. So as always, thank you for coming and participating and asking questions. It's a really good sign. I think, well, it's way more fun for me too, because then I know people are actually watching, right? Yes,
So do we have class the day before Thanksgiving?
yeah, we will have class the day before Thanksgiving. So,
Okay.
if that's an issue for you because of some travel or family stuff, you can just let me know and send me an email, and certainly I understand that. But I'll be here, and we'll have some questions possibly, right, that we can go through, and so you can clean things up. And again, the homework is due on Friday rather than Thursday for this next section,
Okay.
a week from Friday. Anything else? And yes, so late assignments you can still turn in, it gives you officially half credit on the homework. I usually round those up a little bit when I put them into D2L, if you've done done that and caught up. If I've already graded that homework assignment, like put it into D2L, then you just have to send me an email when you've caught up or done some work, so I can go back and regrade it for you, because I don't look back at those assignments unless you let me know. And that's true for everybody and for all assignments. I do want to give you credit for doing them, even if they're late. I think it's really valuable. So I want to give you points for that. So the points are going to help your grade, but also doing that work is really going to help your grade too, right? You're going to learn some stuff that you wouldn't have otherwise. And that's the goal of the course, of course. So yes, you can always go back and do some work. Yeah, the initial question is one that was supposed to be completed in that first week. So it's part of your participation grade. It's sort of staying up with the homework. So that one I don't go back and regrade, but all the homework assignments I do go back and regrade those. And as always, any other questions about your grade, take a look at it, because I have added in a couple of the more recent things, and just don't hesitate to ask me about that. I know that's a concern always for students, and I'm respectful of that. I'm happy with students who care about their grades and their work. That's a good thing, right? You shouldn't ever be sort of embarrassed about caring about your grades, right? Or a point here or a point there, right? That's your work and your scores, and you should get credit for those, right? So let me know if you see anything that's off or doesn't feel right, and we can try and clear that up. Okay. Anything else? And the chat's always a great way.
Do we get points for the rest of the other discussion, not including the one that we missed?
Yeah, so like participating in these or the online discussions.
The online discussion. For the online discussion, do we have to reply back or just like write a discussion post?
The goal is to write something and read a couple others. You don't have to read everybody's, but read 2 or 3 other people's posts. So I can see kind of all those statistics of what you wrote and whose posts you looked at and things like that. And so it's not intended to take you more than 5 minutes, right? On 5-10 minutes to do that.
So do you want us to respond to our classmate posts, or just
I think that's nice. I don't require that. So, it's nice when someone has something to say about things sometimes. But I don't require that. So I do want you to read a little bit, because a lot of the posts are sort of, the idea is that you're saying something that helps you or something that you figured out about the course. And so that's a chance to kind of learn something from somebody else, right? You might say, oh, that was a good idea, or, oh, I see what course you're taking next, or whatever it might be, right? Because we don't have that same interaction that we might in a classroom, right? Where you just can chat with somebody. So that's the idea of those discussion posts. So in terms of grades, I know that's sort of most important. You got to do the posts. It's not intended to be hard. You just got to kind of, do something and think about it for a little bit, and then read a couple of other students' posts, right? So that would give you full credit for those. Anything else? Okay, well, I will let you guys go. I will post the recording of this